Hi everyone, welcome to another episode of Learn With Me series. Let us start today with setting the context in ChatGPT. And now let us dive into the LeetCode 75 as usual. So far we have covered a few easy problems in arrays, in prefix sum, set, queue, and so on. These were all related to the data structures. Right, so let's see if we can solve an algorithm question today. So looks like binary search tree is a good idea. Let's dive into it. Oh, that's a binary search tree. I was actually looking for binary search algorithm. Okay, my bad. Okay, no worries. Let's get into the binary search tree. What does this look like? So we are given a root of the binary search tree. So this is the root of the binary search tree. So before venturing into binary search tree, let's just have a look at what a tree looks like and what are some of the terms associated with a tree. Some things that I can recall are this is every tree has multiple. Oh my God. That's good. Let me just take that, copy paste. That's better. So every tree has multiple nodes. And let's say if this is a tree, the top of this tree is called as the root. So this is the, okay, that does not look good. Let's go here. We say this is the root. And the bottom of this tree is considered as the leaf. So from the root, you can go to the next node this way. Well, basically, I have a tree where each node is connected to two others at the most. Let's just quickly ask ChatGPT, is there anything else that we need to know? Give a basic overview of tree. So I already told I'm asking about computer science concepts, so hopefully it got the context. So a basic unit of the tree is a node. That's what I was referring to, these circles. And then root is the topmost node in the tree. So the topmost node, all the nodes, in this representation, which have a reference in the top direction, this one becomes the parent, this one becomes the parent of this node. So that is the parent, and then there's a child. Then leaf is the last node, which does not have any children. Root is a node which does not have any parent. So edge is the connection between any two nodes. And subtree, height, depth, well, I guess we can skip it for now. Then there are different types of trees. The one that I drew is this binary tree where one node can have maximum 2 children. So this node has 2 children. This node is a leaf node as it does not have any children. So that was kind of a quick refresh on tree concept where there is a node. Root is a node without a parent. Parent and child relation or a connection is called as an edge. Leaf is a node which does not have any children. So there can be trees which are connected to multiple nodes or which have multiple children. So they are called n-ary trees. The drawing was a binary tree. And now the problem that we were looking at is a binary search tree. So what is the speciality of a binary search tree? So basically every node can be represented as the node in a linked list, right? Which has a value and which has a connection to something else. So it could be a connection to the parent, connection to the children. And now in a binary search tree, the values are in a specific order. So let's say the value in this root is 5. Then if we say this is a binary search tree, then this value has to be less than 5. So that's a strict greater than equal to, but for now let's just consider it should be less than. So let's say it can be 4. What about this? This has to have a value greater than 5. Let's say it has to be 6. So basically, if I draw a line from the root, all the nodes that are on this side are lesser than 5, and all the nodes that are on this side will be greater than 5. That is something we know for sure if this is a binary search tree. So binary search tree. Okay, with this idea, so now let's come here. Now I will draw a line at the root. So the same thing goes in the subtree, where all the nodes in this direction should be lesser than 4. All the nodes here should be greater than 4, but they have to be lesser than 5. So let's say it has to be 4.5. This has to be, let's say, 3. Okay. Now let's see an example here. So it is 1, 2, 3 in the subtree, and then you see 2, 4, 7 in this, and you see 3 is also lesser than 4. So basically, I think in this drawing, I could do the other drawing here quickly. So it's one copy, paste, one more, paste. So basically, if I draw a line between these, we know this is a binary tree because it has only 2 children, or at the most 2 children. Then we have select this one, copy paste. Well, how did it look like? So there was one node, that's it. Okay. So this root node has 2 children, and now this, okay. This one had the value 4. This one had the value 2, 1, 3, and 7. Okay. 2. 2 is definitely lesser than 4. Now we come to the subtree here. They say 1 is definitely less than 2, and 3 is definitely greater than 2. But since it comes on the left side of 4, so it comes on the left side of 4, it has to be lesser than 4. So then there was 7, which comes on the right side of 4, and it therefore has to be greater than 4. Yeah, so that is the example. Now what are we asked to do? We are given the root, great, and an integer with the integer values. It doesn't have values such as 4.5, right? Okay. Find the node in the binary search tree that the node's value equals the value that they are providing, and return the subtree rooted with that node. That is quite interesting. So basically, we are given a value here, and we are given the root. So we said, okay, find I want to find the value 3, right? So I'm given access to 4. From 4, I can go to 2 or to 7. Now, since I'm given the value 3, and since I know about binary search tree, I will clearly not go in this direction. I will say, okay, 3 is lesser than 4. So I will see if I may find it in this direction. So I come here. And then we see, okay, this node has a value 2. I am asked to find 3. Clearly, it won't be on the left side. It should be on the right. If it is there, it should be on the right side. So let's go to the right side. Okay, we come to 3. Now we are told that the value to be found is 3 and this is 3. So that is great. Cool. So now we know that's how we can traverse through a binary search tree. I was just speaking in English and showing this diagram here, but how is this traveling from one node to other happening in a binary search tree, right? In an array, we know we have a index value, and let's say we have, so we have an array, and you say array of index 0, then you show the value in the 0th index, right? So array has, let's say, 3, 4, 5 in index 0, 1, and 2. Then you can access each value by adding the index value and accordingly getting that value. But how is that happening here? So we did not go over any linked list yet. It would have been more clear if we did that way. But even otherwise, I think it is still clear just by looking at this structure. So let us look at it. So this tree node is a class. It has a value. So if I want to access this value of a node, what do? Looks like there is no getter method. So I can just do tree node dot val. So basically, if I do root dot val, this is an object of the class tree node, and it has a property called val. And to access the property, I use the dot. So that's how I can get the value at this point. Now, while showing the diagram, I also said I moved from here to here, moved from here to here, and so on. So for that, I need access to these nodes, right? So you see there is an access to those nodes mentioned in left or right. So if I have to go to the right side, then I will do, what should I do? Root dot right, and oh, that's wrong. This is correct. So root dot right and go to the right side. Then I go root dot left and go to the left side if required. Now you see, not if it is a leaf node, the left and right will be null. There won't be anywhere to go to. So those are some things we will have to remember. So that is one part of it, right? So let us break it down to make it easy for us. So we know how to traverse or travel, whatever makes it easier for you. So traverse in a tree given a node. So that is one part of the thing. And we know what BST is. We know all about binary search tree. So if we want a smaller value, we go to the left side, which is over here. And if you want a bigger value, we go to the right side. So that is something we know about BST. What else? So we know how to say if the value is equal or not. We know when to stop the search, right? We know, let's see, at any point, right? At any point, if node.val equal to the val provided here, we stop the search. Or it is possible that let's say we were asked to find the value 8. So we start from the root node because that's what is given to us. The value is not equal. We know in BST the higher value is on the right side. So then we come here. We see the value is 7. Now, if there were any nodes, the higher value would be on the right side, but the right would be null. So we have to stop and say, okay, we didn't find this value. So or we reach a dead end, which is equal to the leaf node found. Yeah, so this is all we need to do to know if the value exists or not. But the thing is, this is just one part of the problem. Why? Because if we do find the node, then return the subtree. They didn't ask us to return the node, but rather return the subtree. So basically, what it means is, if we find 3, oh, I see. If we find 3, we need to send 2, right? We need to send its parent. Okay, let me get this, let me make sure I understand that. So it's in case 2, okay, in case 1, 2 was the answer to be found and 2 was sent. In case 2, the value was 5 and we didn't send anything. Okay. Maybe I got it wrong, I'm not sure. So let's do this and just test it out and see if we got the question correct. So I don't think we need ChatGPT for this. What do you all think? Let's see if we can proceed. Let's see if I remembered the Java syntax. Let's give it a go. So basically we have the root. All right. So what do we do? Okay. If just to make it easier for us, let's say tree node equal to root. So this is the node we are checking for at any point. If node.val equal to val, then what do? Let us just return node. Else if node.val is greater than the val, then if this is greater than what is asked for, we go on the left side. We say node equal to node dot left. So we change the reference for the next search. So else if we say node dot val is less than val, then we go on the right side. So to go to the right side, I need the reference for the right side tree node, so I go there. But this is just the inside search part, right? So this is the inside BST part. Now we need to continue doing this, right? So we need to continue doing this. So while, let's see how to do that. Okay, while node is not equal to null, if we continue, does that look good? The indentation has gone wrong now. Yeah, we can beautify this later. So if we come out of the while loop, we didn't find anything, just return null. I hope. What is stored? If return null. Okay, that looks good. Yeah, let's just quickly. Where is the format code? No, that looks better. Let's run the test case and see if I really understood the question. Now this looks good. I will quickly change this. Can I change the test case? Yeah, I can add a test case. Not maybe I'll add 3 as the value and see what is the expected result. Output is 3. So it looks like that's all we need to do. Sorry for adding additional complexity, right? So we learned the different components, we put everything together, and I think we can just submit and see how that goes. Maybe we missed some edge case. Who knows? What do you think? No? Looks like we did a great job with the runtime. Memory also looks good. Yeah, kudos to us. We went ahead and solved a question in binary search tree. trees are always fun, isn't it so? Thank you so much for joining me today. Hope you had fun. Thank you.